Today we will look at the molar volume, and this is just another concept that has to do with gas laws as we continue. One of the things that we talked about when we first started with gases was that you can measure a lot of different characteristics of gases. So we talked about how temperature, pressure, and volume can be characteristics we can actually measure with gas. So today we're going to look at and reintroduce the idea that the mole, our good friend from first semester, we know that 1 mole equals 6.02 times 10 to the 23rd molecules, and that was something that was probably etched in your memory for a long time from first semester. However, we now also can use the idea that 22.4 liters of any gas, as long as it's at standard temperature pressure, remember standard temperature pressure, then you can actually say that's worth a mole also. So again, Avogadro's number, determine the volume of 1 mole of any gas at STP. It occupies a volume of 22.4 liters, which is a pretty nice size area of volume, I should say. Even though different gases have same number of molecules, they can have different masses. So if we kind of look at this and say this is 22.4 liters of gas, that means that's 1 mole of whatever gas we're talking about. So how does that work? Well, again, STP, so we have STP, standard temperature pressure. So we have temperature of 273 and pressure at 1 atmosphere. So that means that we would have 22.4 liters there. Now that mass of that is going to be quite different for neon than it would be for, say, a diatomic oxygen. So you can see the one thing that changes is the mass, and it has to do with the density of that gas. And as we go to CO2, that continues to change. But also that mass is straight from the periodic table. So if you remember right, oxygen is 16. Just take 16 times 2 because it's 2 of the oxygens, so we have that mass there. Again, 1 mole all the way across the board. The only thing that changes is the mass. So that's going to help us determine a lot of things. So let's start with an example problem. So the example problem we have, number 1 here, and you can, all these things are on your notes as you're taking notes, hopefully. You will see here that it's what volume will 7.29 moles of CO2 gas occupied STP. So you've been given 7.29 moles of carbon dioxide. So which unit multiplier should you use to determine this? The nice thing is you can just use, again, since it's asking for volume, you can say, okay, well, I know what the volume is for any gas. And what's nice is I'm already in moles here. 7.29 was given. So I put moles on bottom to cancel that out. 22.4 liters as my conversion rate, just like I used Avogadro's number. And our answer then would equal 163 liters of carbon dioxide, which is pretty big volume. Let's do another example problem. Let's look at this. This is what is the mass of carbon dioxide gas that occupies 100 liters at STP. Now there is one more step, but the nice thing is you don't have to go to the periodic table. You could, I'm sure, because you remember doing this. But let's start here with 100 liters. That's what we were given right here. And we're going to convert that to our grams of CO2. But what we should do first is convert it to moles, because remember, moles are in the middle. Or moles kind of like the gateway to determining things. So we take our liters here, put liters on bottom because we want to cancel it out. And remember that 22.4 of any gas, liters of any gas equals 1 mole of that gas. And the nice thing is we gave you that from the periodic table. We took 16 times 2 plus 12.01 to equal 44.01. I'm sure you remember doing that. So we'll go ahead and put that in there. And looks like we put O2 on accident, but close enough, right? So 44.02 grams of CO2 equals 1 mole. So again, boom, boom, the moles get canceled out. And then we're left with 196 grams of carbon dioxide. So that's pretty great. We can use then again the mole to determine what our volume is. So if we know this, we can add this to what we already know. But let's do one more. Let's do this in terms of molecules. So we are given 5.25 times 10 to the 22nd molecules. And if we know that, again, 6.02 times 10 to the 23rd molecules, that's a molecule, equals 1 mole, we can then cancel those molecules out. And we can then say, all right, that's going to give us then our next conversion rate, 1 mole on top, 1 mole on bottom, 22.4 liters. And so we just added another step here, and we get 1.95 liters of methane. So again, going from molecules to moles, from moles to liters, looking at volume. So just a two-stepper there. So we can then use something called a dimensional analysis, which we have been, and add it to our stoichiometry skills that we already know. So the first thing we'll always do is write the balance equation. Remember doing that right before Christmas break. And then you say, okay, what do I have and what do I want to know? And then I use this reaction map, which is pretty great. Now, if you remember right, this was the only part we used before winter break. We could go from no, I take that back. We didn't. We used these two right here. We went from grams to moles to moles to grams. And if you remember doing that, hopefully it was something that you mastered and got pretty good at. And as you got pretty good at it, you knew you could start at moles and go to moles, or you could start at grams of A and go moles to moles. And if you remember, I was always taking one thing in the reactant side or the product side and taking it to another reactant or another product. And so then we write our answer after we use this. So you can see here, we can kind of start anywhere. We also used Avogadro's number. So the only thing that's really new is down here is adding these liters. So let's take a look at this. Let's say, okay, this is a balanced equation. We did that. That's step number 1. Step number 1's done. Then I say, okay, write the given quantity and the desired quantity. Well, it looks like I have been given 6.0 moles of H2, and I want to find a volume because volume is measured in liters. So I'm starting with H2, which is right here, and I want to know NH3. Okay, so pretty much I'm starting with moles of A, and A, remember, all the A's are just one certain reactant or product, and then we want to find what the other one is. So this is a pretty simple one in the term, or as far as example problems go. So what's the next thing we need to find? Well, if we want to go from moles to volume, the next thing we have to do, if we're going to moles of one thing to volume or liters of another thing, we first have to stop our layover in moles of B. So we just say, go to my balanced equation. You can see right here the mole ratio. So I go 1 and 3. So my 3 comes from here, and my 1 comes from right here. And that's pretty cool. I can just use that. And then the next thing I want to do is say, okay, I'm going to my volume in liters. So I'm just going to use this unit multiplier right here. And I put my mole on bottom because my mole is on top here. And then use 22.04, excuse me, 22.4 right there, which then equals 44.8 liters of nitrogen. I went from one thing, nitrogen, to the other thing, A to B, in moles, and then I went to liters. Next up, you can see here that I have, again, the same exact balanced equation, so that's pretty nice. I'm starting with a volume right there, 4.29. I'm going to moles of NH3, so that means I'm going from volume of this to moles of this. So I'm going here to here. So I need to go here next. I use the the gateway here, which is 1 mole equals 22.4. There it is. And now I want to go over here to moles. So I go up to my balanced equation right here. And my balanced equation tells me I need 3 moles of H2 and 2 moles of ammonia. And that gives me where I need to go from where I started. And that gives me 0.128. There's 3 sig figs there. I started with 3 sig figs here. Don't forget about that. Next up, I'm starting with a volume of ammonia, and I'm going to a gram, a mass of nitrogen. So what am I doing? I'm starting right here with 15.1 liters of ammonia. Looks like I forgot the 0.1, but that's okay. Again, we're then going to go and use 1 mole of A, 22.4 liters on top, liters on bottom, cancel them out. Where am I going next? I always go across here. I'm going to my moles. I go to my balanced equation. I use 1 and 2. And then next up, I'm going to grams of B. So I go to my periodic table. I know what to do there. I can look at that and determine that the molar mass of diatomic nitrogen is 28.2, 28.02, I can't talk, and multiplying all the numerators and dividing by all the denominators, I get 9.38. So that's just kind of a little more complicated look there. Lastly, let's do molecules because we haven't done that yet. Molecules are starting right here, 4.5 times 10 to the 23rd. Obviously, that's a large number because molecules are really, really tiny. So we always have to go to moles. The moles are the central part of this. We always have to use those. So we'll go ahead and say, okay, that's 6.02 times 10 to the 23rd molecules. So molecules cancel, that equals 1 mole. Cross over, use the balance equation right there. Again, using 3 mole, the molar, mole ratio, I can't talk, of diatomic hydrogen. And then I put that over 1 mole of diatomic nitrogen, cancel out my nitrogens, keep going. I go around the curve here, 1 mole of hydrogen, and that's going to go to our volume, which is 22.4, and I have 50.2 liters of hydrogen.